Okay. Um, so what we're doing is looking at exploratory factor analysis. And to summarize what we were talking about on Friday, it's kind of a strange area because, on the one hand, doing exploratory factor analyses given existing software is really, really easy to do if you ride the defaults. And unfortunately, the analysis that you will do riding through the defaults may not be appropriate for what you're doing. It also does zero assumption checking, and you may overlook some of the important models that you'd like to take a look at. There are the other weirdness about exploratory factor analysis runs almost to the other extreme and says that exploratory factor analysis to be done properly can only be done by hiring a quantitative psychologist like myself to come in and do some kind of occult magic over the numbers and produce an analysis. And the handout that I write here tries to put exploratory factor analysis in your hands, not relying over much on the defaults that were there. And the defaults are there for a reason, and we'll talk about that. But also to provide you with a way of generating a model. Exploratory factor analysis is, in a nutshell, a way of using latent variable models to summarize large patterns of relationships in the data and further the rotation of that solution to a given fit can correspond to maybe a model that you're interested in, maybe a scale you're interested in, but can also correspond to alternative ways to think about your data that a reasonable skeptic might propose. As a class, you seem to like looking at examples and program code. So let's just take a look at, I sent you out an Excel spreadsheet which reads in some data. And what I want to draw your attention to is if you're going to factor analyze things, all you need to do is say proc factor method equals prin for principal axis or principal components and give me a Scree plot, and that's it. And that will give you a printout. And it's very nice. It's very easy to look at that printout. You will get something called an eigenvalue plot that's going to tell you kind of how many dimensions are there. You'll have a picture that you can interpret about how many factors are there called a Scree plot that we'll talk about. And you'll get a factor, a pattern, a whole bunch of factor loadings out of that that are not rotated. And, there, we just did an exploratory factor analysis. Similarly, if we come into SPSS, I can read in my Excel data set as an SPSS data frame, and I can come in to click on Analyze and come down here and select the, dimension reduction, factor analysis, and I'm in the factor analysis dimension, and I can select maybe the words that the particular variables I would like to have. I can ask for some descriptive statistics of the solution, that's fine. And I can factor the correlation matrix or the covariance matrix. I can look at the unrotated solution. And this is, one we'll have a lot to talk about. The default behavior of SPSS is to retain as many factors as you have eigenvalues greater than 1. And there's a history for that as we talk about in the book chapter. But using that criterion uncritically is a really bad idea. Generally speaking, you want to make some determination about the number of factors that you'll be having. If you're doing an iterated solution, that tells us how many factors, how many iterations to do as we iterate our estimates of communality. And after that, there is, various options for rotating the solution. And we'll talk about that. These, SPSS is a little bit behind the curve. These rotation solutions are nice ones, but there are many more that I talk about in the handout that are available on other platforms. So, as I mentioned before, you can then hit OK, and you'll get a factor analysis out very quickly and easily. Here are our communalities. These are the initial estimates of communalities, which were ones. And these are our communalities after we've decided on the number of variables. Here's our Scree plot that tells us how many factors we would have. And here's our component matrix of factor loadings. So I guess I do this not to walk you through it, but just to say it's very, very easy to do an exploratory factor analysis. If we return to where we were last time, heat maps are one way for you to understand where the correlations are in your data. Now, as I mentioned before, if you're hiring the expert to come in and do exploratory factor analysis, very frequently they're thinking about the patterns of correlations. And if you have only a few items in your survey, it's kind of easy just to look at the numbers. But when you have large numbers of items, as in this one, it becomes a little bit hard to think about that. And as we mentioned last time, the magnitude, the color of the dot indicates the magnitude of the correlation. So over here on the right-hand side, we have a little bar that shows the coloration and what correlations that corresponds to. If I'd have a negative number, a negative correlation, I would see that bar extend down there, and there would be another color, I believe red. And if you're doing this inside of R, this is the code that you would need. And it's pretty straightforward in R. And I've also sent you SAS support and SPSS support for doing heat maps inside on those platforms as well. If you're looking at longitudinal data, your heat map is frequently going to look a little bit different. And I put this in just to illustrate that you're not necessarily just going to see squares in your heat map. So in this data set, I've got data across 4 measurement occasions, and I have some scale scores on my reasons for drinking. And you'll notice here that social at wave 0 tends to correlate with social at wave 1 and social at wave 3. These are autoregressive correlations. And the farther I get away from the diagonal, the fainter these tend to become. And that's by the tracing rules, that's kind of what we might expect to see. So if you're using exploratory factor analysis to factor longitudinal data, you might want to think about how your latent variable model will look, or what even perhaps a follow-up confirmatory factor analysis to your exploratory analysis might look like. But this is just an example of how things can look. This particular option that I have doesn't do just dots. It also kind of changes the size of the ellipse to reflect the correlation, a narrower ellipse indicating a tighter relationship. And that's the code that we can use for that. Very frequently, if you're looking at your individual items, though, maybe the items are not going to fall in nice blocks. I mean, this was a nice picture to look at because the items that all dealt with a given topic tended to occur at the same place in the survey. And in your items, maybe they're all mixed up, which is probably better practice experimentally than just doing them block topic by topic. Well, inside of the correlation plot, there's an option to change the order. And this hierarchical clustering algorithm will change the item order so that I can perhaps more clearly see where these relationships are. So this is the output for these items in that hierarchical clustering. So you'll notice that, again, the items having to do with the taste and the physical characteristics of consumption don't tend to correlate with the other ones. But my items are now reordered, and I can more readily see that there's a whole bunch of social and enhanced correlation going on here. And I can also take a look and see that, well, actually some of these social items tend to correlate more highly with the enhancement items than others. In other words, the block of correlations here is not a uniform color. It seems to be a little bit item specific. That gives us one story. That gives us a story about where are the big correlations. But as we talked about in assumption checking for confirmatory factor analysis, this doesn't tell us the whole story. A high correlation may actually mask a different functional relationship. In other words, there might not be a straight line relationship between two variables. And there might be influential observations that give you the correlation that you have. And that's particularly going to be true if you're looking at a relatively small data set. So to that end, another thing that we can do is to take a look at pair plots. So here are some items for the social gathering items that give us some indication as to whether the correlation is linear and as to whether maybe there are some influential observations. Now, this is a very large sample. I used the jitter op, and the items are 4-point Likert scale series. You can see the numbers go from 1 to 4. So you can see where the data are. As we look at this, for the to celebrate item, it kind of seems that, gee, the lowest regression line seems to flatten out for some of these data points. Perhaps what I'm looking at is enjoying a party, people who don't endorse that very much, or people who use the next point. Maybe I could collapse those two things together, and that would give me more of a straight line between these manifest variables and the to celebrate item. And perhaps I wouldn't lose much by doing so, because collapsing these over would just kind of continue the line that I had. Generally speaking, I don't see any polynomial, quadratic curves going on here. And I don't see one or two observations that are really pulling the correlation off. But, this is a way that you can quickly do a whole bunch of low S regressions to examine the assumption of linearity. It's also evident as we're looking at this that we have some significant skew going on. There are very few people who refuse to endorse the enjoying a party item. Let me see now. I can also flip that around a little bit and show the correlations as well, but the code is there to do that if you would like. So let's now talk a little bit about how we get factor analysis to come out and how it is that we actually get factor loadings on all of our factors that span across all the items. In other words, we spent a great deal of time in confirmatory analysis saying you'd have to have things mathematically identified. And if you're doing a straight confirmatory model, I can't, for example, have two factors with arrows pointing at all of the manifest variables. So to play with this, the easiest thing that I can think of to talk about is to consider a correlation matrix of a small set of items. And as we talked about, now we can sort of cash in on material we've had earlier in the class. Eigenvalues and eigenvectors are one way to identify a latent variable model. So an eigenvector, remember, is the factor loading that would result if I constrain the factor loadings, the square of the factor loadings, to add up to 1. The factor variance is an eigenvalue. It corresponds to that identification strategy. So if you go into standard software like SAS and say call eigen, and it will then give you these things that are called eigenvectors. And you'll notice something about them. So this first set of eigenvectors that I have, if I square those numbers and add them all up, I'm going to get the number 1. The same thing happens for all of these numbers. In other words, still at the very end for F8, if I square all of these numbers and add them up, I'm going to get the number 1. Similarly, if I just use that function, I'm going to get these things called eigenvalues. So these correspond to the factor variances in that model. And to give an interpretation of what we're doing, these eigenvalues are roughly an indicator of how many variables worth a particular factor is. So as I'm looking at this, I might say, well, if I'm just factoring the correlation matrix, it maybe isn't worth it to invoke a 4-factor solution because that doesn't even explain one manifest variable's variance. And that's just kind of a rough way of interpreting it and an introduction to the default behavior of retaining eigenvalues that are greater than 1. So if I go from, the computer spits out these eigenvectors and I've got these eigenvalues, I can use those numbers to generate the factor loadings that you would see from a standard factor analysis program. Specifically, the principal components that you're going to see in SPSS or SAS can be taken by taking the eigenvectors and dividing each of those by the square root of the eigenvalue. I'm sorry, multiplying them. So 0.41 times the square root of 3.72 gives me 0.79. And those would be the numbers that you would see if you said proc factor or inside of SPSS, if you selected the loadings that come out of there. So the component solution is a data summary technique. I have put 1s on the diagonal. I can, in principle, extract as many factors as I have manifest variables in the data set. And it's an automatic procedure. Computer programs spit them out automatically. This doesn't help you understand how it is that these numbers came to be. And given that we spent quite a bit of time talking about path analysis, I thought that I would use path diagrams to show you where those numbers came from. So starting out, let's take a look at our initial correlation matrix that we have. We have 1s in the diagonal. And if I want to generate the numbers that I saw above, I would fit the following structural equation model. So this 0.79, that 0.79 is equal to what I see above, 0.79, 0.79 that the computer automatically spit out. This first unrotated factor gets first crack, so to speak, at the whole correlation matrix. So the numbers here do the best job they possibly can at explaining all of the correlations in the data. Now, you might say, well, how do we then go about to get the second factor? Well, what I do is I now fit a second model in which I fix all of these numbers to be the values that I had in the first component, and I now freely estimate a new factor. And this is how a factor analysis program goes about giving you a set of numbers in which every variable loads on every factor. Now, because this first component was done first, this is going to do the best job of replicating the correlation matrix. This component is only going to be able to have loadings that explain additional variance and covariance in the manifest variables. And this is why you're seeing that some of these loadings are negative and some of these loadings are positive. And that's the way it has to be, because in this step one, we fit the correlation matrix as well as we could. So this is essentially factoring the residual correlation matrix left over. So to look at that, here's our first component. And if I use the tracing rules, I'm going to get this as my predicted matrix. So taking these numbers, 0.79 times 1 times 0.79 is going to give me 0.62. And 0.79 times 1 times 0.79 is going to give me 0.63 within rounding error. And 0.79 times 1 times 0.66 gives me 0.52. So I subtract the original correlation matrix that had ones on the diagonal, and this gives me this residual matrix. And this is the matrix that is factored to produce these matrices of second component loadings. Now, if this were a classroom in the real time, I could look at the classroom and I could say, well, are you talking too fast or are you talking too slow? But I don't see any video cams, so I can't even read faces. But is this making sense?
Last question.
Yeah.
I just want to check. It seems to me that we need quite many variables to do factor analysis. Like for the example you saw, like two factors, both egg variables for two factors.
Mm-hmm.
So is there any kind of like uh, minimum number of variables to have like two factors or
That's a
one
great
factor?
question. Well, let's go back. I mean, let's go back first and talk about the parsimonious chapter, parsimonious factor model chapter that we had before. If you have, say, three variables, you can only extract ever one factor. If you have four variables, you could extract two correlated factors. You could extract a model in a random intercept factor model where you have one factor that has loadings that are freely estimated and another factor that has loadings fixed at one. If you have five variables, you can start to extract two factors again. So, I mean, that's kind of the way the numbers go. And the results out of an exploratory factor analysis and the number of factors that you identify depends in a critical way on how the magnitude of the correlations in the data. So it could be that if you have, say, psychophysiological data, blood pressure, things that are measured with a relatively high degree of precision, that is where the communalities are high and the uniquenesses are low, you could extract more factors reliably and identify the models better than if you had a correlation matrix where the relationships between the items were relatively weak. And at that, in the case of having many, many items and perhaps even a large sample, your question becomes kind of a dual issue that maybe some of the items have such low correlations with all the other items that I wish to drop the items from the analysis altogether and not try to rotate given items to that solution. And we'll get more into the guts of this, but that's kind of the answer. I mean, very frequently you do want to go in and do a heat map maybe, because that would flag those items for you that just don't seem to be doing anything at all, and you can drop them before you get into the exploratory factor analysis model and looking at the dimensionality. And looking at the low S curves would also help you to maybe rescale your data so that you have linear relationships and hopefully higher correlations. And that would give you a better outcome when you start extracting factors and rotating them to some solution. So that's kind of the big picture. To me, the purpose of talking about this now is that I'm using confirmatory factor analysis to show you where the numbers come from that you see in a data set. The other thing to notice about this path diagram that I'm showing you is that notice there are no error variances present in the diagram. There are no slings on these manifest variables. Exploratory factor analysis assumes that measurement error has been removed from the model in the process of estimating the factor model. And we'll talk about how that happens with iterated components later, but that's another way in which it differs. But the nice thing about it is this all more or less follows the same logic of the tracing rules and reproducing variances and covariances as we had. So is that kind of a long-winded answer?
Okay, thank you.
Okay. Anything else?
Can I ask one more question?
Yeah, the room's pretty quiet. Yeah.
So maybe it's I don't know, it's a correct question or not. So like would it good if we start by exploratory factor analysis and go to confirmatory factor analysis, like get
Very,
the
very,
factors before?
very frequently we do. I mean, it's important that you tell the reader exactly what you did. So, I mean, this is kind of an ethics thing. There's nothing to stop you as a researcher in this day and age to doing an exploratory factor analysis and finding a model that has nice loadings and then fitting a confirmatory factor model and publishing the confirmatory factor model without telling the reader what you did. Well, that's really kind of evil practice because it's possibly the case, especially if you're looking at a data set with only a few hundred observations, that you capitalized on chance. So, I mean, it doesn't necessarily add to your manuscript to say, I did an exploratory factor analysis, I did the following rotation, I did the following examinations, and based on that, I identified the factors that you see in the confirmatory model below. Here's how it fits. And you could even put some of that detail into a reviewer's supplement. And that's probably a better way to go. Or, I mean, professionally, at this point in your lives, you're going to be writing a master's thesis and or a dissertation. And you'll need to, the crazy thing about dissertations is, yeah, you're writing something that's going to be about 100 pages. And it needs to be a creditable example of, I know what to do with the computer and I know what to do with research. But you also have to kind of think in the back of your head, how can I shorten this, the central message of my dissertation, down into maximum about 20 pages of text? And that's a big challenge. So, I mean, you may want to end up presenting a confirmatory model, but this is what God gave us technical appendices and dissertations, is you can go back and put all of that detail in, and you can refer reviewers to it when you submit your article. Anything else, gang? Right. So if we were to talk a little bit more, the way that I'm getting these eigenvectors and eigenvalues out, these eigenvectors, the first eigenvector is going to be bigger than, the family of eigenvectors, than the second family of eigenvectors. And the second family is also going to be characterized by positive and negative loadings. And that's just mathematically the way things get extracted. one of the nice things about making a PDF is we continue this same issue. Oh, the other thing I wanted to talk about is something called the trace. If I add up all of the numbers in a principal factor solution, the diagonal numbers, that gives me the eigenvalue. And that's just another way of getting it mathematically. And the trace is a fancy word for summing all the diagonal elements. So if I carry this process forward and extract 3 unrotated solutions, it's the same thing. I fix all the numbers for component 1, I fix all the numbers for component 2. That gives me a predicted correlation matrix. And the residual matrix then is what I use to extract component 3. Well, notice that the numbers are going down even relative to component 2. They are, again, mixes of positive and negative numbers. And the positive and negative numbers are, again, kind of roughly half positive and half negative from the negative numbers and the positive numbers that I had in component 2. And I can then extract a 4th component. And again, that's fixing all of these numbers and freeing all of these numbers. So that's where the numbers are coming from in SPSS or SAS or R. That's how the computer program is doing it in the background for you. Now, as I said before, this is a problem because I assume that the communalities are 1, that all of the variance in that variable belongs in my factor model. And that doesn't meet the assumption of how we think about our variables. Namely, we like to think that there's some error variance down here. So what we're going to do now is, instead of having 1s on the diagonal, we're going to stick in a communality estimate. We're going to stick in a number that will represent something from 0 to 1 that indicates the proportion of variance in the manifest variable that is due to the latent variables that are responsible for the phenomenon. Now, the way that computer programs, people writing factor analysis programs, begin is the number that they stick in is called the squared multiple correlation. And if you go back to Appendix A, there's a reason why squared multiple correlations are kind of nice to look at. Mathematically, they're pretty easy to compute. So a squared multiple correlation is going to be, I guess I can come down here, is going to be the proportion of variance in a manifest variable that is explained by reference to all of the other variables you have. So if you did a regression predicting item C, this makes social gatherings more fun, and had as your predictors all of these other manifest variables, the squared multiple correlation you would get would be 0.7645. And in the same fashion, if this is the criterion and all of the other items are their predictors, you're going to get this as a squared multiple correlation. So this becomes a new model, a new set, actually a variance covariance matrix, kind of a funny one, that I can then use the same models, the same math on to extract factors. So if I do what I did before, that's going to give me the following eigenvectors if I'm factoring this squared multiple correlation matrix, and this is going to give me my factor loadings. And these are the default numbers over here on the right-hand side that a factor analysis program like SPSS or SAS or R will give you in their results, in their unrotated solution. Now, over here, if we're looking at our eigenvalues, notice that I've got a slightly different picture than I had before. In other words, now I've got some negative numbers for eigenvalues out here. So, eigenvalues correspond to a factor variance. I can't have a negative variance on a factor. And for that reason, inside of factor analysis programs, this becomes the absolute largest number of factors you could ever possibly extract. The shape of this eigenvalue plot is still kind of the same as what I had before. I have a very large first factor and kind of a middling second factor. And I'm only factoring 8 variables, and I kind of know that they're both from 2 separate subscales. So more generally, now let's turn to the question in exploratory factor analysis of figuring out how many factors we have. And as I've mentioned in passing before, we decide on the number of latent variables we have by looking at how big the eigenvalues are. And as I showed you in SPSS, the default behavior is something called the Kaiser criterion. And that is just to say, I'm going to retain as many factors as I have eigenvalues greater than 1. And this was, back in the day, a reasonable default for a computer programmer to say, because what other number are you going to use? But even Kaiser back in 1960 said, this criterion is not going to tell you exactly how many factors are there. It'll tell you maybe what a lower bound is. And he also says that it's only appropriate if you've got components analysis. That is, you have core ones on the diagonal of the model, and it's not appropriate if you're doing exploratory factor analysis. Excuse me, my parrot seems to be making a lot of noise this morning. So, there's a lot of people out there who would say, don't use eigenvalues greater than 1. If we're going to take a look at what that Kaiser criterion looks like in action, we can go back to our reasons of drinking example back on page 261, and we can make a plot of the eigenvalue by dimensions plot. And here's what one looks like. So, and the Kaiser criterion would say, this number 1, if you have an eigenvalue bigger than 1, I'm going to keep it. And if it's less than 1, I'm not going to. And that's basically all there is to it. But there are other decision techniques that you can have. So many of the programs like SPSS will do something called Velicer's map test, in which we take a components analysis and we look at partial correlations. And the squared correlations are the average squared off-diagonal correlations in that matrix. In the first step, we take out a component and we partial out all of its items. In the second test, we take the squared off-diagonal correlations and then keep repeating this as many times as we have in the data set. So this is a CAN procedure that you can use in the software that you have. If you're playing with R, this is the VSS package. If you're playing in SAS, proc factor will do the Velicer test, and SPSS will also do it, but only in the more recent versions of SPSS. So if we're looking at the map test results, this is what it looks like. You get these numbers out, and you take the lowest value as indicating how many factors you should retain. So by Velicer's map test, that's going to say we need 4 factors. A second way of looking at an eigenvalue plot is to go back to Catel's idea of a Scree test. Well, what's a Scree? If you're a mountain climber, you can, I remember the first time that I visited some family friends in Utah. You can see the Rocky Mountains for a very long ways away, but even by train, you're still going to be a day and a half away from the mountains. Before you get to the mountain, before you're climbing the mountain, rocks start to happen and maybe small outcroppings. This is called Scree. And the idea of a Scree approach is that the researcher is looking for an elbow in the data. And you're going to take as your number of factors one less than that elbow. So if we come back to our picture again here, this is clearly my mountain. And maybe, at this point, this is maybe the beginning of my Scree. Mechanically, what people often do is they'll just visually look at the eigenvalue by dimensions plot and say, gee, it looks like there's a Scree here. If you want, there are computer programs that will physically calculate a statistical model of the Scree. And the way that works is what we'll do is we'll take the first two factors and we'll calculate a regression line. And we'll take the first three factors and we'll calculate a regression line. And at the point that, including another variable, that regression line changes, that's going to be our identification of the Scree. So that's a way of making a judgment about how many factors are there. Sometimes people will argue that you should take maybe a slightly larger number of factors that are indicated by the Scree. And the reason for that is maybe your factors that you're extracting or going to rotate to are correlated. So even if the Velicer map test and the Scree test and maybe your eyeballs tell you there's only 4 factors, you might want to entertain analyses that look at 5 factors. More recently, it's possible to generate models that build on the idea of parallel factor analysis. So parallel factor analysis is the idea that I can take a data set and I can randomly permute my data and calculate an eigenvalue plot of that. So if you're playing about this with R, eigenboot parallel is the program that you'd play with. And a second approach that's kind of similar is to calculate a correlation matrix based on your data and then randomly generate a multivariate normal distribution and factor that. And if you're playing with R, FA parallel is what you'd look at. The bottom line here is that these simulations based on random data will give you one idea about an eigenvalue by dimensions plot, and your data give you a different one. So the idea is, if I scramble my data set, if I look within a column and I randomly order it, I've broken the data on one person, because what I've done is I've taken maybe observation 1's score on the first variable and observation 10 score on the second variable and observation 36 on the third variable. That's now one row. And I'm factoring that. So that should, in theory, break all of the correlations in the data. Well, you're still going to get some spurious correlations going on because of skew in the data. So the way you interpret it is you get these little boxes, and at the point where the eigenvalues for my random permutation are significantly above what I find in my data, I come back and say, oh, that's going to give me 4 factors. So in this data set, here are the eigenvalues I have in my data. And if I do this this simulation of a normal distribution given the correlation, I permute that, these are the highest 95% values of eigenvalues. And if I permute the data, that is, if I take each column of data and I scramble it, I order it randomly and make a new data set and keep doing that, these are the eigenvalues I'll have. In this case, this entire line of eigenvalues looks pretty similar regardless of my simulation strategy. But it's all more or less pointing to the question that, this is pretty close to, the maximum number of factors I'd want to extract based capitalizing on chance. And FA parallel and the other programs I have generate these for you.
I have a question.
Yeah.
So for the fifth component, eigenvalue, the real eigenvalues are below 1, but simulated and permutated ones above 1. So what would we choose in this situation? Should we include the fifth one or drop the fifth component, the fifth factor?
Can you repeat that again?
So I said the eigenvalues for fifth factor was below 1.
Yeah.
And then the simulated and permutated ones are above 1.
They're still above 1, right?
Yes. So how do we decide whether we include the fifth factor into the analysis or not?
Oh, okay. Well, we can think about it this way, maybe. If I had, so I'm having ones on the diagonal. If I had perfectly random data, my correlation matrix would look like a 1 on the diagonal and numbers very close to 0 on all the off diagonals. If I factor that, I'm going to get ones just straight across the board because each factor is going to explain only one variable. It's going to explain it completely, but it's only going to explain one variable because there's no covariances in the data. Now, by chance, the reason that these little boxes in the diagram that you're looking at go very gently from slightly above 1 to slightly below 1 is when you're extracting those eigenvectors, you're capitalizing a little bit on chance. Not that much because this is a large sample of about 2,000 people, but nonetheless, there's some chance you can capitalize on. If you're factoring a smaller data set, like 300 or 500 people, the plot that you're going to see is going to look a little bit more dramatic. That is, the first few factors that you have in your simulations are going to look like they're substantially above 1. And this is because each correlation in your data set can capitalize a little bit on chance. So, the picture won't be quite as, flat as you're seeing it in here. And, I guess that also highlights the point that even if you have random data using the eigenvalue greater than 1 criterion, you're going to identify some factors in the data even when no factors are actually present. Is that getting where you at your question, Zara?
Yes.
Okay.
Thank you.
All right. So if we were looking at, I guess, a parallel analysis, this is, for a smaller sample size of only 200 people, this is what our model looks like. So, here's our permutations. And as you can see, the slope of this line is substantially larger than we had before, and the two simulation strategies look a little bit different. So this is, again, the permutation. That is, I take each column of my data and I scramble it by randomly reordering it, and I do that for all my variables. And this is the simulation strategy, where I take the correlation matrix that I have and I randomly simulate that. So because I've only got 200 observations here, this gives me a substantially different picture. If I were factoring only these 200 people, I would probably end up concluding I have only 3 factors in the data, because this eigenvalue in my data is below or pretty darn close to what I have in my randomly generated data. So that's and that's basically what's going on. So if we were to summarize the eigenvalues that we have, these are our plots, and this is why we're kind of agreeing that we'll have 4 factors in the data, because the eigenvalue was always larger than my parallel analysis eigenvalues, and it continues to drop. And again, the reason these eigenvalues turn negative is because I do not have ones on the diagonal. I've got squared multiple correlations going on. And this is my summary statement toward the end, and then it'll probably be kind of a good place to stop before we go on to iterated solutions. We have many ways of figuring out how many factors are present in the data. And based on these models, it kind of looks that we have 3 and maybe 4. If we were thinking about our analysis, we'd go back and take a look at our correlation matrix and say, well, from the eyeball test, it really kind of looks like 4. And when we actually selected items for the measure, we also kind of had 4. So maybe the reason we're getting 3 sometimes is 2 of these factors are really correlated. And there are no what we call clear, bright lines of guidance. It's a judgment call. Now, Lim Jahng and his student Lim recently did a very nice paper, and they talked about parallel analysis and different models that you could look at. And their basic idea is go ahead and do your parallel analysis, or use the other tests for that matter, to determine factors, but you also probably want to explore plus or minus 1 around that in evaluating a model. And that was really kind of a nice paper because they dealt with simulated data. And it seems to be nice guidance for researchers in the real world. So that's a reason why in our particular case, we might want to consider 3 factors, 4 factors, or 5 factors in the data. Okay, that's a lot of talking for a Monday. And the next topic that we'll get into is, okay, we did a factor analysis. We made an initial choice based on the number of factors, but all of that was contingent on using either ones on the diagonal or a squared multiple correlation. And we know by the tracing rules that if we come up here to a factor solution, that the communality of this variable is 0.79 times 1 times 0.79 plus minus 0.35 times 1 times minus 0.35 plus 2.5 times 1 times 2.5, for example. And that's going to be a number that's different than the squared multiple correlation. So what we'll do in our next topic of iterative improvement of communality is we're going to use the numbers from our factor analysis to update the communality and redo the factor analysis. All right, I've run us a little bit over, but that is